All right, are you ready for this? The last lesson, and probably one of the shortest ones, if not the shortest one of the course. This is the last application of integrals that we'll look at, which is how an integral can be used to find the average value of a function. And it's got a couple of examples here, and that will be it. So if you look right here, this probably looks more complex than it really has to be, but I'm saying that if you find the integral of any function between 2 points, and you really, multiplying by 1 over b minus a, that's the same as just dividing the whole thing by b minus a, which is the same as dividing the whole thing by the distance between these two bounds. That tells you an average, which makes sense. It's like a mean, an average of something, a mean. And how do you find the mean of something? You add up a bunch of values and then divide by how many values you have added up. Well, the integral here is the sum of all these values, and then we divide by the difference between the beginning and the last bound. And so the fact that this comes back to this represents an average value of something is actually not surprising. And so let's just use it. So I have some function here, and again, this function in red, y equals x over square root of 3 plus x squared. I want to look at just the region from 1 to 3. So from 1 to 3. If I want to find the average value of all these points here, what's the average of them all? Now again, we can't literally add up all the points here because there's an infinite number of values, both to add up and then, divide by infinity. You can't do that. So that's why I can't just literally find the average in using the mean like you would have learned in grade 8. But I can find the average like this. By adding up the integral aspect, we'll add up all the total values. And then this, dividing by b minus a, or 3 minus 1 in this case, will essentially, it's like dividing by all the total values. And so let's just do it. So it looks a little bit messy at first. But I have 1 over b minus a, or 3 minus 1, times the integral from 1 to 3 of this function, x over root 3 plus x squared dx. All right. And so, 1 over 3 minus 1 is 1/2. But really, most of my work is let's find the antiderivative here. And again, I need to use substitution. So I'm going to say let u equal 3 plus x squared. So du would then be 2x dx. And as usual, I look at this, I look at this. I pretty much got everything I need. If I just squish a 2 in there and put a 1/2 right here. There you go. Now everything works out. And so 3 plus x squared is my u. And again, I'm going to ignore the 1 over 3 minus 1 for a moment. I'm going to focus on my antiderivative. So focusing on the antiderivative, I have the integral of 1/2 of just u to the negative 1/2 du. And using our power rule, I have 1/2 times 2u to the positive 1/2 plus some constant. And we've done this sort of stuff before. That cancels out. I have just u to the 1/2 plus some constant. Or I have 3 plus x squared, square root of that, plus some constant. There's my antiderivative, root 3 plus x squared. So that's what I want to integrate from 1 to 3, and then essentially just divide by 2. So now I can deal with this part. I can actually integrate this thing here. And so I want to take root 3 plus x squared. I want to integrate it from 3 to 1. And then eventually take all that and divide it by 2. 3 minus, 1 over 3 minus 1. I'll do that later on. First, let me do this. And so this equals root 12 minus 2. When you substitute the 3 and the 1 in. But that's it. Going back to write this part right here, right, which is the same as 1 over 2. which is just the distance between 1 and 3 here. And so I want to take this whole answer and divide it by 2, or divide it by 2. And again, I'm essentially done here. It does clean up a bit, so I'll do that. But this will represent the average value. And so if I clean this up a bit, root 12, same as 2 root 3, minus 2 divided by 2. Everything has a factor of 2 I can take out. So I have root 3 minus 1. That is the simplest answer. And so root 3 minus 1 is the average value of this function between 1 and 3. And really, all we did was find the shaded region here. That was most of our work. That is all of this right here. And then divided by 2, because 2 was the total distance between the beginning and the end. All right, and so the last question is kind of more of an applied question, because right now, what does this root 3 minus 1 really mean? Well, nothing, really, because it's just some random function. But here's a model of something, of the, the scatter plot shows you the population of Canada over the 20th century, every 20 years, and the curve in green is a regression equation. That models it quite well. You can see the equation, the regression equation right here. So I can tell that X must stand for the years since 1900, Y must be the population of Canada in millions. All right, so we can now, I want to use what we just were talking about to find the average population of Canada in the last half of the 20th century, so since 1950. How can we do that? Well, 1950. So really, we want to find what's the average population of Canada in this range from here to here. So we're going to do the same things as before. We're going to essentially find the area of this whole shaded region, which in itself doesn't really make any sense in this context. If that number there represents the total, I'm adding up all the different populations year after year, but that in itself, that number doesn't really represent anything useful. But then divide by the number of years, 50, and that will tell me something that is quite straightforward, the average population of Canada in those years. So let's do it. I want to start by finding the integral from 50 to 100, because I want the last half of the 20th century of the regression equation, which I'll just write down here, 15.7 times e 0.x minus 11 dx. Keep in mind years is years. X represents years from 1900. And that number there, again, that represents the area under that curve, which in itself is not really the most useful number. But if I go 1 over 50, or I guess I can do it, I'll do it in 2 steps. 1 over 100 minus 50, which is the same as taking that whole integral and dividing by 50. That will now tell us the average. Okay, so with that said, like before, most of my work is really dealing with the integral, which I want to break my integral up into 2 parts, because the integral of negative 11 is really pleasant, because negative 11 is a constant. Over here, I'll do a little bit of substitution. And again, this part here, the 1 over 100 minus 50, or just 1 over 50, I'll deal with that at the end. In fact, I'm just going to change to 1 over 50 right now. Okay, so focusing on what I really care about. The integral here, I'm going to just focus on antiderivatives here for a bit. And so I have 15.7 times e to the 0.01x dx minus 11 dx. Actually, I'll put our little bounds back in. Okay, I can see right now that this is going to be 11 times 50. There's 50 units on the x that we're going up. Each time it's 11. 11 times 50 is 550. So that all of this right here is 550. So again, I won't forget about that. Maybe I'll put it down here. There we go. I don't have to think about that anymore. Now I can focus entirely on this part right here. And I'm presuming that's my inside function. So I'll say let u equal 0.01x, which means du equals 0.01 dx. And so I can make that work right here if I just go 1 divided by 0.01 1 right here. Now that said, this part right here, 1 divided by 0.01 is the same, is exactly 100. 1 divided by, same as 1 divided by 1/100. It's 100. And I like the number 100 better. So I'm going to take that 1 divided by 0.01 and just write 100. All right, so now focusing on, again, the integral on the left, I have 100 times 15.7, actually the 15.7, let's take that out too. So take out that 15.7 out of the integral. 15.7 times 100 is 1,570, even better. There we go. Integral of just e to the u, du. And the antiderivative of e to the power of u is e to the power of u. And then times 1,570. And I want to integrate this from 100 to 50. Although, again, that u, remember, is 0.01x. So maybe I'll just change that right now. And since I'm dealing with actual data here, clearly at some point going to a calculator is not a bad idea. The good thing is, you don't actually need the calculator right away because 100 times 0.01 is 1. 50 times 0.01 is a half. And so I get 1,570 times e to the power of 1 minus e to the power of a half. Go to my calculator now, and this leads me to 1,679.21 approximately. Keep in mind, let's now think about what we have here. That represents this right here. That's this integral right there, or this part right here is that. And so I'm pretty much done, as long as I don't forget that I have to subtract 550 from that. 11 times 50. And this number here is not terribly helpful. This number here is 1,129.21. This number here is the area of the shaded region from here to here. That's what I just found, which doesn't really make much sense in terms of a useful number in this context, because it's the total. It's not the total population of Canada in those 50 years. It's like the population of one year added to the next for 50 times. So that number there in itself isn't very relevant. But once I divide by 50, the number of years here, right, or this multiply by 1 over 50, it's all the same thing. Once I take this and divide by 50, now I have an average that comes to about 22.6 million. That number is fairly easy to understand. That's the average population of Canada, according to our model, from 1950 to the year 2000. And again, looking at our data, the model is pretty good. So that means my average is probably pretty accurate. And as usual, the actual integration here wasn't that much work. The numbers were a bit messy because I had a real regression equation here. But aside from that, the integration part wasn't terribly complex, although a little bit messy at times. And hey, yeah, I'm done. You don't have to hear me talk anymore. Goodbye. Farewell. All the best to you.